So as I was saying that sometimes like some of the associations, like we can't really explain like why it's like positive. So if you see that in the interpretation part where it says that the average prior sentence increases the number of errors, uh, it's a positive association. Usually we would think that if it's a positive, uh, like if there is a prior sentence, like if someone has been penalized before, and if that sentence is like longer, okay, then people would be like, ideally we would think that people would commit less crime, and as a result they would get arrested like a lower probability, right, in terms of the probability. So here's a question mark. So sometimes these kind of things we really need to be careful when we are trying to interpret. Okay, if it is not the way that you want, there might be a reason. Those reason could be maybe the model was not a linear form, or there's some issues with the model. So those things we have to be really careful. Okay. So, and there is, if you look at the R square value, it's only 0.04. Okay. So it's only explaining 4% of the variation of the y, or the dependent variable. So it's being explained by the explanatory variables, or the x variables. So R square is like really low. But there's a general remark, and you have to know that even if R square is small, regression may still provide good estimates of the ceteris paribus effects. Okay, so you like, although we ideally want that the R square to be as big as possible, but just because you have a small R square, it doesn't necessarily mean that you cannot like run a regression. It can still give you a good estimate. Okay, so I can ask this type of questions in the final, like suppose we have a small R square, can we still get a good estimate from the regression results? So the answer would be yes. Like even if it is small, it still can give a good estimate. Okay, so you can write any papers, like whatever models you guys are selecting in the, like from the worldbench database, you have so many databases. You can select your own model. Even if you get a low R square, you can still run a regression and get a good estimate of it. Okay. So just like the simple regression cases, we have some assumptions for the multiple regression model. So assumption 1, it has to be linear in parameters. Okay, it's the same. So it has to be linear in the parameters. Okay, which means that the relationship between the y and the explanatory variables, which is in this case the x's, there are so many x's, right? We have x1, x2, xk, they should be linear. Okay, that's the assumption number 1. So it's similar to the simple regression model. Assumption number 2 is that the data is a random sample drawn from the population. Okay, so each data point therefore follows the population equation. So it also has to be a random sample. Okay, same like the simple regression model. Okay, and of course we also have these error terms, if you noticed. Okay, now the assumption number 3. This is the most important one when we are doing a multiple regression like analysis, that there should be no perfect collinearity. Okay, so what does collinearity mean? It means that none of the independent variables is constant, and there are no exact linear relationship among the independent variables. So let me just go back to the slide. If, for example, if x1 and x2 or xk, these are a constant values, then we won't get a good, we won't even do a basic like interpretation. Like similarly, like there should be variation in x. When I was talking about the simple regression model, right, I said that the x should be varying. If everyone in this class have same GPA, then what kind of regression can we run? We can't run any regression, right? If we are plotting, like all of you guys would be GPA like 4, and it won't be a linear form, it would be a point. So there should be variation in the x. Not only that, like x's should be it can't be constant. It cannot interfere with the other x's. So x1 cannot influence x2, x2 cannot influence xk, or vice versa. Okay, so this is known as multicollinearity. Okay, in fact, I talked about this in previous classes. Like I said that like ability cannot influence, let's say, your education level. So you can think x1 as your education and x2 could be ability, right? Now if we have similar type of variables in the model, then there is a problem with multicollinearity, right? Can we keep similar variables in the model like education, ability, because they influence each other? Higher capable you are, your education level will go up, right? And if you have a lower education level, that means you have a, most likely you have a lower ability. Okay, so we cannot keep similar variables in the model. One way to, although it's not in our course, but since I have shared the do file with you guys, one way we can adjust that is using the instrumental variable technique. Okay, so how does the instrumental variable technique work? Let me just give you guys an example. Okay, it will get clear in fact. So let's just write an equation. So wage rate is equals to, let's say, beta 0 plus beta 1 education plus beta 2 ability plus the error term u. Okay, now this model, does it support the third condition of the multiple regression analysis, the regression method? No, right? Because ability, like here, ability, the x variable is affecting your education level. Agreed? So if that's the case, then we cannot make any inference or interpretation from this model, like if one is influencing the other. So what I can do is I can use an instrumental variable technique. So instead of education, let's find a thing that is proxy to an education, but that does not have a direct relationship with ability. So let's think about a proxy variable for education. What could be a proxy variable for education that is not affecting ability? Something like class attendance, right? So if we find a proxy variable, we replace it with the proxy variable. So class attendance has nothing to do with your ability level. You either come to class or you don't come to class, but class attendance can give a signal that you are taking education, right? So we can use class attendance instead of education. We replace it in the model, and when we estimate the coefficients, we may get a better estimate of the wage equation, and we have addressed the multicollinearity problem, right? And this technique is known as the instrumental variable technique, because we are replacing the education with an instrument. And what's the instrument? The instrument is class attendance, right? So if you can do an IV, in fact, in some graduate level courses, like in some schools, in good public state schools, like IV is usually used in the graduate level courses. Okay, in the undergraduate level, nobody is expecting that you guys know what an IV is, but because I thought that it may be interesting, because in the future, like in 1 or 2 years, you guys would, maybe some of you guys would think about going to a grad school, but you already know what an IV is. Okay, if you want, we can do some lab sessions, show how an IV works. Okay, so why do we use an IV? Why? If I ask, like, why do we use an instrument variable? It's because if there is a multicollinearity in the model, which means that the independent variables or the explanatory variables, in this case x1, which is education, and the x2, which is ability, if they are correlated with each other, we cannot make any inference because one is influencing the other. So it will become a biased inference. So to reduce the bias, an instrumental variable is used. Although I am not going to ask maybe in your exams, because it's not in our syllabus, but it's a good idea to know why we use an IV. Okay. Is that clear? Okay. So if you don't understand, please let me know as soon as possible. Okay. But these techniques are important. So remarks on the assumption number 3. So the assumption only rule out perfect collinearity correlation between explanatory variable. Imperfect correlation is allowed. So imperfect correlation means that perfect correlation is like when it's directly affecting one another. Like ability is directly affecting your education, right? It's one-to-one relationship. But if it does it in an indirect way, then it's not a problem. So indirect way could be if I use class attendance. So class attendance indirectly affects your education, and that affects your maybe higher education will improve your ability in the long run, right? You become more capable as you learn more things, right? As you take more courses, you learn more statistical courses, more softwares, your skills increase. So imperfect correlationship is allowed in this case. We can allow imperfect correlation, but direct correlation is it violates the assumption number 3. So if an explanatory variable is a perfect linear combination of the other explanatory variable, it is superfluous and may be eliminated. So if both ability and education is in the model, you would want to eliminate one of them because they are similar types and they have a perfect linear relationship. And constant variables are also ruled out. Okay, constant variables are also ruled out, because we said that the x's should have some form of variation. So if they don't have any variation, then inference or interpretation would be difficult. So they have given an collinearity example. They are saying that if you look at this equation, so average score is dependent on the expenditure level as well as the average income level of a household. Now, expenditure and average income is somewhat correlated, right? If the household is rich, if their average income is higher, they tend to spend more on their kids' education, and that would increase the average score for the kids. So this is an example of perfect collinearity. Also the example that I use, education and ability, right? That is also another example. Okay. So another example is this voting. So you guys can read the textbook. In fact, you can try to find a copy of the textbook online. Like try to search the textbook name. Maybe you might get a 5th edition or something like that. But still, you can read the like notes, the theories, if you don't want to purchase the book, because I usually upload the book with the problems, right? So you don't need the 6th edition. You can go to Amazon and buy like 5th edition, 4th edition. It will be cheaper. The 6th edition would be expensive. So as long as you guys can read the theories, it's fine. Okay. Assumption number 4 is the same as the assumption for the simple linear regression. It's the zero conditional mean. That means the explanatory variable must not contain any information about the mean of unobserved factors, or the unobserved factors is the error term, right? So if your independent variables have information about the error term, then assumption 4 is violated and we cannot do multiple regression analysis. So 3 conditions are exactly similar except the condition number 3, which is the perfect multicollinearity. Because in the simple regression model we only have one explanatory variable, right? We don't have multiple explanatory variables. For example, they have given an example of a zero conditional mean. So if average income was not included in the regression, it would end up in the error term. It would then be hard to defend that expenditure is uncorrelated with the error. So if there is another problem here, if we remove average income, okay, I said that you cannot keep similar variables in the equation. So if I remove average income, then what's going to happen is that the average income would be in the unobserved part, right? Because you have excluded the average income from the model. If you exclude that, then it goes to the unobserved part. In that case, expenditure would be correlated with the error term, right? In that case, x1 given u is not equals to 0. It's not 0 anymore. That's why we need to use instrument variable. Okay, you cannot just remove. First step is we cannot keep similar variables in our model. But even if we keep similar variables in the model, even if we don't keep similar variables in the model, still it can influence the error term, right? So that's why we also have to be careful about that. So it's better to use an instrument variable to address all these problems. It can address the problem of multicollinearity. It can also address the problem of zero conditional mean. So instrumental variable has a powerful technique. Right? So explanatory variables that are correlated with the error term are called endogenous. You will often hear professors saying, like if you take like a advanced level econometrics class or a graduate level course, professors will say that the model is endogenous. Okay, what they actually mean is that it is correlated with the error term, your explanatory variables, right? So that is endogeneity. Okay, is that clear? So when you write your paper, you should also make sure that you should write that, yeah, we have tried to address endogeneity problem in your model. So how did you try to address that? By looking at the zero conditional mean, right? And making sure that your model does not have any multicollinear terms. Okay, so you should write that how you have addressed the endogeneity problem. Okay, So if endogenous explanatory variables, that is the x variables, are uncorrelated with the error term, then it is exogenous. And in fact, for any regression, it has to be exogenous in order to carry out the regression. Okay, that means the error term should be uncorrelated. It cannot be correlated. It should be uncorrelated with the explanatory variables. So we like the exogeneity factor. Okay? Because exogeneity would ensure the unbiasedness of the OLS estimator. Okay, so I can ask like to ensure the unbiased of OLS estimator, what is the condition? Right? What is the condition to for the unbiasedness of OLS estimators? The key condition is that the error term should be uncorrelated with the explanatory variables, or in other words, it should be exogenous. Okay. So unbiasedness is an average property in repeated samples. Okay. And when it is unbiased, only then your estimated beta hat j is equals to the population beta j. Okay, only when it is unbiased. Okay, is that clear to all of you guys? Like when would be the estimated beta j would be actually equal to the population beta j. The estimated is the sample estimate, right? And original beta j is the population beta. Yeah. Okay, now like we talk about including irrelevant variables in a regression model. If you recall, last class I said if you have more explanatory variables in the model, then what's the outcome, or like what happens to the R square if more explanatory variables are added in the model? Yeah, as Michael has said, if we add more explanatory variables in the model, the R square becomes bigger, right? Maybe you want a bigger R square, but for that, if we just include any irrelevant variables in the model, like if we use all 360 variables from the health nutrition database of the World Bank dataset, it won't make any sense, right? I have said this many times that we can't just add any irrelevant variables in the model. Okay, and the main problem with like putting irrelevant variables is that it increases the sample variance. Okay, that's the problem. That's why we don't want to add nonsense variables in the model, because that increases the sample variance. Okay, why we care about the variance? Why variance is important? Because variance would help us get the standard deviation, and if we get the standard deviation, we can calculate the standard error. So we want the standard error to be as small as possible, right? We don't want a large variance or a large standard deviation, and as a result the standard error is bigger, then it's a problem. If standard error is bigger, then many of your coefficients would become insignificant. So small standard error is good for getting a significant coefficients. Okay. So key point is we can't include irrelevant variables in the model, because that increases sample variance. If sample variance increase, then the standard deviation increase, right? And if standard deviation increase, the standard error increases. So only include the important variables in your model. Okay. Now there is another thing called the omitted variable bias. Now because of reducing the sample variance, if you say that okay, I will just include only one or two variables in my model, Now that is also a problem because that would cause the omitted variable bias. You may exclude one of your most important variable from the model, right? That is also bad. You can't just like remove the variables just to reduce the sampling variance. Is that clear? So you have to have a balance. Like keep the important variables, but do not omit any important variables from the model. Like you are trying to estimate wage. For wage, education is an important variable, right? You have education, work experience in your model. Now because you want to reduce the sample variance, you are saying that okay, let me remove education from the model. That's omitted variable bias. You have like excluded one of the most important variable, right? Because education captures your wage level, right? How much education you have would capture your wage. Okay. So here, if you look at the problem, x2 is del 0 plus del 1 x1 plus v, and this v is also some sort of like an error term. So instead of x2, if you plug this in your model, like del 0 plus del 1 x1 plus v, we have two x1 terms if you observe carefully. One is the beta 1 x1 and another comes from this del 1 x1 beta 2, right? Because if x2 is del 0 plus del 1 x1 plus v. So if y is only regressed on x1, this will be the estimated slope on x1. In that case, if you see that it is estimating a bigger x1, this coefficient becomes bigger, right? Because you have removed x2 from your model. If you remove x2 from your model, x2 is in terms of x1. They might have an indirect relationship, right? And once you plug back into the x2 for like x2 is plugged back here. Now when you are estimated only x1, your coefficient would be bigger in size, because now there is not only beta 1 but also beta 2 del 1, right? And where is this beta 2 del 1 coming from, Brandon? It's coming from this x2 variable, right? Because you didn't include the x2 variable. So the x2 variable has an indirect relationship with x1, and once you plug that back in, you are getting this extra beta 2 del 1. As a result, your estimated x1 coefficient is now bigger. Previously, it would be only beta 1.
So does that mean that the error term is like influencing the model now?
So now the error term, because there is an omitted variable bias, so it is increasing the coefficient and it is a biased coefficient. If you delete the education from the wage equation, if you are trying to estimate, let's say, wage W equals to beta 1 education plus beta 2 let's say work experience, right? You delete, like, let's say, education, then education would have some sort of relationship with work experience, right? If you are well educated, you might have a higher level of work experience, okay? But that's like an indirect form, may not be like directly related. It can be the other way around as well. Like if you take more education, you forego a lot of work experience. So it can have either positive or negative relationship. But then the coefficient will have some form of work. So when you estimate beta 2, that would be greater, right? Because you have omitted and one of the most important variable from your model. So this slide is important. In fact, I might ask you, like, give an example of an omitted variable bias and how that is biasing the like the coefficients. So it is biasing by beta 2 del 1. I will give you guys this component, like x2 equals to this. Okay, you have to plug back in the model and then show that when you are estimating x1, now you have this extra, this is the extra term beta 2 del 1, right? In fact, let me give you guys an example here. Let's do it in class so it will be clear. So wage equals to beta 0 is the constant, beta 1 education plus beta 2 work experience, okay, plus error term. Now let's assume that you excluded beta 1 education, and we know that beta 1 education equals to beta, let's say instead of beta, let's say C0 plus C1 beta 1 education plus an error term, let's say the V. So I would want you guys find the bias when we are estimating beta 2 work experience. So what would be the bias in this case? You have to plug this beta 1 education, this thing, right? Let me use this. Let me use a bigger one. You have to use this, plug it back here, right? Because beta 1 education you have deleted from the model, right? So if you plug it back here, in fact, I made a mistake. This should be beta 2 work experience. C1 beta 2 work experience. Okay. So if you plug it back here, what would be your beta 2, new beta 2 term? It would be beta 2 plus C1 work experience, right? Because you now have an extra C1 term. So you are overestimating your coefficient by C1. Isn't it a bias? What do you guys think? It's definitely a bias. So you can't exclude an important variable from your model. Okay, that's the moral of this story. Like, education is a key indicator of estimating a people's wage. How can you exclude that variable? It doesn't make any sense. You exclude it, then if the beta 1 education is C0 plus C1 beta 2 work experience plus V, it's like overestimating the work experience coefficient by C1. Is it clear to all of you guys? Right? Mike? Michael? Okay. So that's the moral of this story. Okay. So Brandon, it's clear, right? So you can't do that, and this could be a classical final question. Like, give an example of the omitted variable bias, and I will give you guys, if you omit that variable, then what's the problem? Okay. In fact, you guys can read this example on slide 21. Okay. It will give you guys a good hint. In fact, they use the same one I used, like education, but instead of work experience, they have used ability. Right? So read slide 21. yourself, you will understand what they are trying to say. Okay. So more general cases, slide 23. We should know the direction of the bias, whether it's overestimated or whether it's underestimated. Okay, so that is important, the direction of the bias. Okay. So if let's look at the example of omitted variable bias in a wage equation. If you see, this wage is related with education, is related with job experience, it's also related with ability, right? So if experience is uncorrelated with education and ability, then the direction of the omitted variable bias can be analyzed in the simple two variable case. Okay, so they are saying that experience is not real correlated with education or not correlated with ability. In that case, the bias can be explained only in a simple two variable case. We can treat it like a simple two variable case. They haven't detailed that, but if you see that ability and education are kind of positively correlated, right? So if they are positively correlated, if you remove one of them, then usually the direction of bias would be upward and it would be overestimated, right? So let's look at the example before, the slide 21. We are overestimating the education correlationship, right? Because we have excluded ability from the model. If you exclude ability from the model, ability and education have positive correlation. So if there is positive correlation, it would overestimate the education by beta to del 1. So if the correlationship is negative, if it was a negative correlation, then it has a negative sign in front, then it would be underestimated. Is it clear? So usually the relationship, if it is positive, it would be biased upward. If there is a positive correlation, biased upward. If it's negative correlation, bias downward. Right? Is it clear to all of you guys?
You're just saying overestimating, underestimating.
Yes, bias upward means overestimating, and bias downward means underestimating. So if ability was like negatively correlated with your education, which is not, because it's not negatively correlated. Usually ability is positively correlated. So if you omit one of the important variables, it will make it overestimated, like biased upward. Okay, these are the terms that they use in statistics. Okay, although it's not maybe in this textbook, like they use the direction of bias, but that's how we interpret. Okay, so next is the homoscedasticity assumption. Like the homoscedasticity assumption in a simple regression model, we also need a constant variance. Okay, and it should not contain any information about the unobserved factors. Okay, must not contain any information. So variance should be constant. So you guys can say, okay, most of the assumptions are similar with a simple regression model, except for the multicollinearity assumption, right? But this assumption may be hard to justify in many cases. Okay? Although we want a constant variance, sometimes it's not possible to justify it. And for calculating the variance of a multiple regression model, this is the formula. Okay, this is how we actually calculate the variance. So now let's talk about the components of OLS variance. High variance would increase the sampling variance because there is more noise in the equation, right? I already told you guys that we don't want a high variance, right? For a high variance, it increases the sampling variance, right? And there is more noise in the equation. A large error variance makes the estimates imprecise because if they have a large variance, that means a large standard deviation and a large standard error, and large standard error would make the estimates imprecise. Okay, so if you have a high standard error, let's say you want to find that smoking is an important variable for estimating people's total health expenditure, right? So in that case, you want the smoking variable to be significant, right? But if you have a high standard error, the smoking variable will become insignificant. That is the reason why many of the variables, like if you recall in the lab session when we ran the regression, only maybe one variable was significant, right? And we got the constant variable also significant, right, in the Stata lab session. But sometimes you want that at least 2 or 3 of your variables to be significant, right? So when you write your paper, let's say you have 5 or 6 explanatory variables like x variables, and you have y, the only one dependent variable, right? But if you don't find any significant variables, do you think that people would get interested to read your paper? No, right? So try to select, not only select variables, but try to model in such a manner that at least 2 or 3 of your variables become significant. Okay, if you writing a paper and from the Stata output you say none of my variables are significant, then what interest do I have to even read it? Like what policy implication do you have for the paper? Like why are you writing it then if none of your variables are significant in your model? The reader will lose interest, right? So you are not giving any policy suggestion. It's like, yeah, smoking is insignificant, BMI is insignificant, or access to clean water is insignificant. Then I will like why did you even write it if all of the variables are insignificant, right? So to make it significant, we need a lower standard error or lower variance in the model. We don't want too much noise. Okay, and so don't include like nonsense variables. Like if you include like 50 explanatory variables which doesn't make any sense in the model, it will unnecessarily increase your variance and all of your variables will become insignificant. So if you like sometimes some students say that professor, I am not getting any significant results. So when I look at their model, they have included 5-6 extra variables which doesn't need to be in the model. Like if they use 10 explanatory variables, you lose the power, okay, because you are increasing the variance unnecessarily. So more sample variation, but there should be variation in the explanatory variable, okay, which is the x variable should be varying. If you find a data set where, like, especially if we are seeing, like, we are looking at countries with high education level in Europe, right? If all the countries have education level 90% and above, is there a very lot of variation in the model? No. So include some countries with low education level as well when we are estimating like an equation or regression, right? So include like countries, like if your variable, that means your explanatory variable, the x variable must have variation. Like let's say BMI, if the BMI of the countries are similar, it's a problem. There should be variation. African countries will have most likely lower BMIs, right? Because more than 40 to 50% of people in Africa are like lacking in nutrition and things like that. So their BMI will be lower, right? So include more variation in the explanatory variables. Okay, that will give you a precise estimate. And it increases with the sample size. That's why I took, if you recall, I took 100 and something countries, 170 countries or something like that, right? Last time I told you guys, if we take 30 countries, what's the problem? Not much variation. And if these countries are in the same continent, in Europe, the variation would be even lower, because all these European countries are similar in nature. Their education level is similar, their income level is similar. If the variation is similar in that case, then the estimates won't be, not much precise. That's the limitation of a regression model, like a simple regression or a multiple regression. So increasing sample size is also good. Okay. So increase sample size, increase variation in the x, the explanatory variable. But that doesn't mean you include any x variables, like 100 x variables in the model just to increase the sample size. Okay. That will increase the variance of the model. So variation and variance are two different things. Variation is the how much variation is there in x, the explanatory variables, the variables that you have interest. Let's say I have interest in estimating people's income. Okay, so income is I want my data to have a lot of variation in the income variable. But that doesn't mean I would include income. I will include, let's say, wage. I will include like tax. All the variables in the model will increase the variance of the model. Okay. So maybe just we include whatever is necessary. Okay. Do not include nonsense variables. And linear relationship among the independent variables. Okay. So linear relationship is required. But if the linear relationship is like one independent variable is affecting the other independent variable, like if ability is affecting education, then it's a problem, right? Then it can lead to multicollinearity. We have discussed this like in the previous case. Again, they are giving some examples of multicollinearity. You guys can read the slide 37, slide 27, sorry. Okay. I don't want to repeat same things. Okay. So why is this a multicollinearity? They have teachers' expenditure, they have material expenditure, and they have other expenditure, right? So when you have different types of expenditure in the same model, this is also a problem of multicollinearity, right? And so it would be hard to estimate the differential effects of different expenditure categories, because all expenditures are either high or low. So for precise estimates of the differential effects, one would need information about situation where expenditure categories change differentially. Okay, so we have lot of expenditures in our model. Not only they are linearly correlated because they are type of expenditure, right? So if teacher expenditure goes up, maybe expenditure for instruction materials will also go up, right? And other expenditures might also go up as a consequence. So if they have some sort of relationship, or it could be the other way around. If let's say Wayne State is increasing the teachers' tuition fees, so if they increase the tuition fees, then they have less resources to spend for textbooks and things like that, right? Then it can also have like a negative association. So it can be positive or negative. Okay, it really depends. But at least they have a linear relationship with each other, and they can cause multicollinearity in this example, right? So in this above example, it would be probably better to lump all expenditure categories together because effects cannot be disentangled, right? So in other cases, dropping some independent variables may reduce multicollinearity, but this may lead to omitted variable bias. So to reduce multicollinearity, what we did is we lump all the expenditures together, right? So if you lump all the expenditures together, then they are not variables that are affecting each other in the model. So you have reduced multicollinearity, but now you have created some omitted variable bias because you have some variables which are not in the model anymore. So it's really a choice, like what you should do. Again, in this course, they haven't talked about the instrumental variable technique, okay, which I am focusing again and again. That can solve both multicollinearity and that can solve both omitted variable bias. Okay, so okay, and estimation. Only the sample variance of the variables included in multicollinearity will be inflated. Estimates of other effects may be very precise. Note that multicollinearity is not a violation of MLR3 in the strict sense. Multicollinearity can be detected through variation inflation factor, okay, VIF. So this is the formula. So if you have multicollinearity in your model, in Stata, you guys should write in the command prompt, if you type VIF, it will tell if your model has multicollinearity or not. If a VIF is greater than 10, that means your model is suffering from multicollinearity problem. Okay, so note it down because you guys also, like, you can't just run a regression in your model and tell me that yeah, it is perfect, it doesn't have any multicollinearity, or it's a perfect estimate. You have to check the VIF test first. Okay, so if the VIF is greater than 10, then unfortunately your model has multicollinearity issues. Okay, so if you want, let's do a sample like example in Stata. Let me just make it bigger. Preferences, wider, larger font. Okay, command prompt is here. So let's just import, or in fact, let me just download one of the datasets that I used in my intermediate macro. Okay, this is my paper and my dataset. I will share my paper and dataset with you guys. Okay, that will give you an idea how to write a paper. And so health data Stata set 13. You can open this. So if we look at the model, so in my model, let's say I want to do regress. So I type regress and health expenditure. And let's say health expenditure is my dependent variable, right? When you put regress and first health expenditure, it's the dependent variable you should put first. Now I want to see how overweight, male smoking, literacy rate affects the health expenditure. Okay, so 3 explanatory variables and 1 dependent variable. So I regress it. I get a pretty small r square. I get the overweight coefficient to be positively like related. Smoking is negatively related with health expenditure. Literacy rate is negatively related with health expenditure. That means higher the literacy rate, your health expenditure goes down. Higher the amount of smoking, your health expenditure goes down. Kind of, I mean, makes sense if you think that if you're smoking more, you're dying early, so the government is saving money. This health expenditure is the health expenditure of the nation. Okay, if you're overweight, then your health expenditure goes up. That also makes sense. Like it's a positive relationship. But we need to check if they have any multicollinearity problem. So we write VIF, small VIF. And if you see the values are 1 point something, 1 point something. So is there any multicollinearity in the model? As long as the value is less than 10 or less than 5, it doesn't suffer from any multicollinearity problem. But let's see what happens when we include similar type of variables. So regress health expenditure. I put male smoking, female smoking. Both are similar type. They have cross relationship, right? If the male is smoking, maybe the female would smoke more, right? Because if they're living in the same, because she can be a secondary smoker, right? Now let's run the regression and run a VIF. Fortunately, the VIFs are not. I expected that the VIFs would be larger, okay, but maybe the dataset designed in such a good manner that they were not correlated, okay. But in some cases, you will see that they have high. So let's do another one. Health expenditure, overweight. Let's say ln of overweight. I put 2 types similar of them. And now, what's the VIF? So one is overweight, another is the log of overweight. Both are similar type variables. What's the VIF now? Greater than 10. Is the model suffering from multicollinearity? Yes. You can't include similar type variables in the model, right? Overweight and ln of overweight are exactly the same thing, right? It's just a different form. So when you choose your model, make sure you guys don't have similar types of things in the model. So that's one example of multicollinearity, and we tested using VIF. Let's test the homoscedasticity. So I type head test. So it doesn't have any homoscedasticity because we can't reject the null. So the null is constant variance. P-value is small. Okay. Sorry, if p-value is small, we have to reject the null. Right? P-value small means reject the null. So in this case, if we reject the null, null says constant variance. Reject the null means there is no constant variance. So this model is not only suffering from multicollinearity, but it is also suffering from homoscedasticity problem. So it doesn't, it's heteroscedastic in nature. It's not homoscedastic. So I am writing a comment. It is not homoscedastic. So it, in other words, it's heteroscedastic. Okay, I am saving the do file for you guys. So copy, let me create the do file, and I'm putting in the Dropbox folder. So chapter 3. Okay. And let me share my data set also there so that you guys can see my data set. So it will be in the Dropbox folder. So it's at the sample data set 2 or health data set. So I have saved my data set, my do files in our shared Dropbox folder. Many of you guys might not have Stata. Okay, so that's a big problem if you are thinking that how do I write my a paper if I don't have Stata in the first place. What I recommend is go to our lab. You guys don't have the one card access, but you can ask our secretary that can we get the access. As long as you guys go from 9 to 5, 9 a.m. to 5 p.m., they will allow you to use the lab. Okay, so use the lab and use data from there. Okay, or if you want, you can purchase like a 6-month trial or something like that from the Stata website. But I recommend that if you want for free, go and use our lab computers. Okay, we have like 14 lab computers. So go there, run your regression, check your VIF, variation inflation factor. Head test is for the heteroscedasticity. Okay, I have saved the do file. I have saved my. Let me also share my paper with you guys. You will see how it's done. Okay, so let me see, copy. Intermediates, intro to statistics and econometrics, destination folder, content, links to embedded file. So you guys should have the folder now in your Blackboard. Let's check if it's there or not. All right. So audits paper and dataset. You can let's see if the paper works. You can also look at the paper presentation. Yep, I have included my 26-page paper. Read it and see how I have used it. Right, the modeling and the citation. I also have the codes, so you can do the codes as well. So you basically can replicate my paper just to have a feel, but don't just submit the same paper to me, then it's no new contribution. Try to replicate my paper, read my paper. It will give you a basic idea how to do a cross section. Okay, so I have attached my codes, my dataset, everything is there. Okay, so yeah, so that's the variation inflation factor. Okay, and do not share the resources without my permission. Your friends, I'm more than willing to give it to them. Okay. So variance in the misspecified models. So misspecified is this estimated model one, which is the omitted variable bias. Right? Okay, that's why it's misspecified. And we can calculate the variance in misspecified models using these two formulas. If you use irrelevant variables, your variance of your estimated model is greater than the it's greater, right? So do not include irrelevant variable regressors. That's the case one. And in the second case, if you are reducing the number of variables in the model, that will give you a lower variance, but then your estimates would be imprecise. Okay, so that's the trade-off. So when you are reducing the variance, you delete an important variable, that's an omitted variable bias. But if you do an omitted variable bias, then variance would be lower, but your estimates would be imprecise. Okay, so these are the two cases. So this is another formula of estimating the error variance. You guys can copy these formulas in your final exam. Okay, I'll give some homeworks from chapter 3, so that will help you use these formulas. Right. So again, some formulas of the standard deviation. Okay, important one is this one. This is the homoscedastic assumption. It's in slide 32. Slide 32. We have to ensure that the variance is constant. Okay, the second last slide. Efficiency of the OLS estimator, which is the Gauss-Markov theorem. So the OLS estimator would be unbiased if assumption 1 to 5 is satisfied, right? It should be linear in form, random sampling, no multicollinearity, zero conditional mean, and homoscedastic, which has constant variance. Okay, so once these 5 assumptions are met, only then OLS is unbiased. So this is the key. I can ask why, when is the OLS estimate unbiased, and when does it satisfy the Gauss-Markov theorem? Then you guys should mention these 5 conditions. Okay, I can say that mention the 5 conditions. So you guys have to write that. All right. And once it follows the Gauss-Markov theorem, we call the OLS estimator as the best linear unbiased estimator, or we call it blue. Okay, so I can ask, when is the OLS estimator's blue, or is the best linear unbiased estimator? Only when it follows these 5 assumptions. Okay, so that's about chapter 3. Okay, and I have shared my resources. Feel free to watch them and try to do it in your free time. Okay.